Unit 18 Statistical Inference Tests of Hypothesis. Contents 18.1 Introduction, 18.2 Statistical Inference Statistical Inference, 18.3 Cases, 18.4 Tests of Significance, 18.5 Conclusion. Learning objectives. It is expected that after reading Unit 18 you would be able to draw statistical inferences on the basis of the concept of probability. Use the tool of statistical inference to test hypotheses. Apply the tool of statistical inference for estimating the unknown parameters of the population under search. 18.1 Introduction. Unit 18 deals with the statistical inference, which uses the concept of probability to explain the element of uncertainty in decision making. You would find that though it occupies a lower status among statistical tests, you would be able to use chi-square test is a wide variety of researchers. If you have a relatively smaller sample, it would be better to use students test, that is parametric test. You would learn in Unit 18 in detail about both the chi-square and students tests. For hypothesis testing, Unit 18 is going to prove to be the most helpful in the mini research project that you have to complete as part of your assignment of MSO2. 18.2 Statistical Inference. Statistical inference uses the concept of probability to deal with uncertainty in decision making. It refers to the process of selecting and using a sample statistics to draw the inference about a population parameter based on a sample drawn from the population. Statistical inference takes care of two classes of problems. A. Hypothesis testing. It tests some hypothesis about the parent population based on the sample drawn from the population. B. Estimation. It uses the statistics obtained from the sample as an estimate of the unknown parameter of the population based on the sample drawn from the population. A. Hypothesis testing. It begins with an assumption called a hypothesis test that one makes about a population parameter. Steps in testing a hypothesis: formulate a hypothesis, decide an appropriate significance level, select a test criterion, carry out calculations, make decisions. Let us discuss in brief each of the 5 steps. 1. Formulate a hypothesis. First of all, a hypothesis is set up about population parameter. Thereafter, sample data is collected, sample statistics calculated, and the information is used to assess how far the hypothesized parameter is correct. Examining the differences between the hypothesized value and the actual value of the samples mean test the validity of an assumption. Conveniently, rather than a single hypothesis, conventionally, rather than a single hypothesis, two are constructed. These hypotheses are constructed in such a way that if one hypothesis is accepted, the other is rejected. The two hypotheses are called null hypothesis, designated as H0, alternative hypothesis, designated as HA. In the simplest form, a null hypothesis states that there is no true difference between the sample statistics and the population parameters. It asserts that the observed differences in accidental and or unimportant arising out of the fluctuations in sampling. A researcher, for instance, who wished to test whether the annual per capita income in a community is higher than 10,000 might formulate the null and alternative hypothesis as under. Null hypothesis H0, mu is 10,000. Alternative hypothesis HA, mu is greater than 10,000. Another instance, as researcher might wish to test the mean difference between the annual per capita income of two groups. In this case, she might formulate the null and alternative hypothesis as under. Null hypothesis H0 is mu minus mu2, that is equal to 0. Alternative hypothesis HA is equal to mu minus mu2, is sum is 0. 2. Decide an appropriate significance level. The next step is testing hypothesis is to set up a suitable significance level to test the validity of H0 and against HA. The confidence with which a null hypothesis is adopted or rejected depend upon the adopted significance level. Figure 18.1 Acceptance or rejections of null hypothesis two-tailed at 5% and 1% respectively. This is the graph, the rejection region, and this also rejection region, acceptance region. This is 0.95 percentage, 0.95 95 percentage. So this is acceptance region here, where mu is 2.58 in the plus side, and here mu is 2.58. This is 1% probability level. Here is 5% probability level is there. Conventionally, the significance level is expressed as a percentage, such as 5% or 1%. In the former case, it would mean that there is 5% of rejecting a null hypothesis, even if true. This means that there are 5 out of 100 chances that the investigator would reject a true hypothesis. Third is select a test criterion. The next step in hypothesis testing is to set a test criterion, an appropriate probability distribution that can be applied in selected for the particular test. Some of the common probability distributions are percentage 2, percentage square, T and F. Let us see later. Carry out calculations. Computation is carried out of various statistics and their standard errors based on sample. Make decisions. In this step, statistical conclusions and decisions are made to reject or accept the null hypothesis depending on whether the computed value falls in the region of acceptance or rejection. See case 1 and case 2 in 18.3. Reflections and actions 18.1. Let us say that you are carrying out a research that has both the null and alternative hypothesis. You need now to set up a suitable significant level to test the validity of null hypothesis as against the alternative hypothesis. For this task as well subsequent task, follow the procedure given in the text. Next, you would need to set up a test criterion. For this purpose, select an appropriate probability distribution that can be applied for a particular test. Then carry out computation of various statistics and their standards errors. Now, based on sample statistical conclusions, make decision to reject or accept the null hypothesis. This would depend on whether the computed value falls in the region of acceptance or rejections. Work out the steps in concrete terms of your own research project and incorporate them in your research work report. 18.3 cases. Case 1. If the hypothesis being tested at 5% level, the observed result has probability of less than 5%. Then the difference between the sample statistics and the population parameters is significant and cannot be explained by chance alone. Thus, the null hypothesis or H0 is rejected, and in turn, alternative hypothesis HA is accepted. Case 2. If the hypothesis being tested at 5% level and the observed result has a probability of more than 5%, then the difference between the sample statistics and the population parameters is not significant and can be explained by chance variation. Thus, the null hypothesis is accepted, and in turn, the alternative hypothesis is rejected. In hypothesis testing, it is important to understand the following: one-tailed and two-tailed test of hypothesis and type 1 and type 2 errors. One-tailed and two-tailed test of hypothesis. Depending upon the research problem, the null and alternative hypothesis are defined in such a way that the test is known as one-tailed or two-tailed. A two-tailed test of hypothesis will reject the null hypothesis if the sample statistic is significantly higher or lower than the population parameters. Thus, in a two-tailed test of hypothesis, the rejection region is located on both the tails and the size of the rejection region is 0.025, whereas the central acceptance of region is 0.95. If the sample mean falls within mu plus or minus 1.96 SD, that is in the accepted region, the hypothesis is accepted. If on the other hand it falls beyond mu plus or minus 1.96 SD standard deviation, then the hypothesis is rejected, as it will fall in the rejection region. Let us take an example of two-tailed hypothesis. Suppose a researcher is interested in knowing whether there is a gender difference in IQ. You can formulate the following hypothesis: IQ of females is equal to IQ of males, null hypothesis. IQ of female plus or minus IQ of males, alternative hypothesis. Or in other words, IQ of females may be lower or higher than that of males. So if it is put in this graph, figure 18.2, two-tailed and two-tailed test of hypothesis, A and B are one-tailed, whereas C is two-tailed. See, this is A is one-tailed, and there is probability is 0.05 rejection, so one side only. Okay, here is the higher side or B is in the lower side. Here both the side rejection is in the both sides, so it is called two-tailed hypothesis. So in contrast to the two-tailed hypothesis, in one-tailed hypothesis, the rejection region will be located only on one tail. In this case, the size of the rejection region will be 0.05. If one is in testing hypothesis at 5% probability level, if the sample means falls above mu plus 1.645 SD, case A in figure 2, or below mu 1.645 SD, see in the case B figure 8.2, then the hypothesis is rejected as it will fall in the rejection region. Let us make an example of one-tailed hypothesis. Suppose a researcher is interested in knowing whether the IQ of female is higher than that of males. In this case, you can formulate the following hypothesis. IQ of females is greater than IQ of male is null hypothesis. IQ of female equal to IQ of males alternative hypothesis. Second is type 1 and type 2 errors. First, as researcher's decision is correct when a true hypothesis is accepted and the false hypothesis is rejected. One-tailed and two-tailed test of hypothesis and type 1 and type 2 errors. Here H0 is true, H0 is true, acceptance is true and rejection. The correct decision accept and choose true. So this type 1 and type 2 errors is in testing a hypothesis. Type 1 error is designated as alpha, whereas type 2 error is designated in beta, and it is important to note that both types of errors cannot be reduced simultaneously, as a reduction in one leads to increase in other if the sample size remain unchanged. Thus, if type 1 error decreases, type 2 error will increase. In most of the statistical tests, the level of significance is fixed to 5% probability level. This means that probability of accepting a true hypothesis is 95%. Sometimes the level of significance is fixed at 1% probability level. In that case, the probability of accepting a true hypothesis is 99%. In this case, accepting a false hypothesis will also increase. Reflections and actions 18.2. Carry on this hypothesis testing with the same example as you have taken in reflection and action 18.1. You need now to carry out both one-tailed and two-tailed test of your hypothesis. A two-tailed test of hypothesis will reject the null hypothesis if the sample statistic is significantly higher or lower than the population parameter. In a two-tailed test of hypothesis, the rejection region is located in both the tails and the size of the rejection region is 0.025, whereas in the central acceptance region is 0.95. In contrast to the two-tailed hypothesis, you would notice that in one-tailed hypothesis, the rejection region will be located only in one tail. Similarly, you would need to carry out the type 1 and type 2 error test. Designate type 1 error as alpha and type 2 error as beta, as pointed out in the next text above. You need to remember the both type of errors cannot be reduced simultaneously, as reduction in one leads to the increase in the other if the sample size remains unchanged. If you follow the text in the section 18.3, you would be able to carry out both sets of tests in the hypothesis of your research. Make sure to include them in your research work report. 18.4 Tests of significance. Chi-square test. Chi-square test Chi-square is probably the most commonly used of all non-parametric tests. It is applicable when data are nominal and grouped in categories. You can examine the difference between the observed and the accepted frequencies. Chi-square is equal to sum of O minus E all square by E, whether O and E are the observed and expected frequencies respectively. The calculated value of chi-square is compared with the table value of chi-square for given degrees of freedom at a certain specified level of significance, example 5%. If the calculated value of chi-square is higher than the table value of chi-square, then the difference between the theory and observation is considered to be significant. On the other hand, if the calculated value of chi-square is lower than that of the tables of chi-square, then the difference between the theory and the observation is considered to be non-significant. As mentioned above, while comparing the calculated value of chi-square with the table value of chi-square, one has to determine the degrees of freedom. The degrees of freedom is the number of classes to which the values can be allocated at will or arbitrarily without defining defying the limitations or restriction. For instance, if one has to choose 4 numbers whose sum is 100, the freedom of choice exists only for selecting 3 numbers, and the fourth is selected automatically. If, for example, the first 3 numbers are 14, 26, 32, then the fourth is fixed as and must be 28. 100 minus 14 plus 26 plus 32. In this case, the degree of freedom is 3. Chi-square is used for a variety of purposes. Also, there are numerous tests that are close to chi-square. Here, the test of goodness of fit and the test of homogeneity or association are presented. Test of goodness of fit. Test of goodness of fit. We often want to know whether the observed frequencies are in agreement with the probability or expected theoretical distributions or not. The following steps may be followed. Step 1. Define null and alternative hypothesis. Step 2. Decide probability level. Step 3. Estimate the expected frequency for each category based on theory and probability. Step 2. Calculate chi-square. Step 5. Determine the degree of freedom. Step 6. Compare the observed chi-square with the tabulated chi-square. Accept or reject the null hypothesis. See box 18.1 for the examples. Box 81.1 examples test whether a form of transport is favored more significantly than another. So, mode of transport frequencies. So, observed, expected. Car, bus, retro, scooter, train and total. So, observed is 18 and expected is 20. So, solution is here is that null hypothesis, there is no significant difference in the choice of type of transport. Alternative hypothesis, there is a significant difference in the choice of type of transport. Type 2 probability level of the hypothesis testing is 5%. The expected frequency is 20 in all the categories is based on the fact that there is an equal choice of type of transportation. Calculation. Chi-square is equal to sigma O minus E all square by E. So giving that values, all these values, you will get chi-square is 0.5. Step degree of freedom, here's k minus 1, that is 5 minus 1 is equal to 4. The table value of chi-square is at 5% probability level and 4 degree of freedom is 4.95. The calculated value of chi-square, that is 0.1, is lower than the table value of chi-square. Thus, the number of hypotheses is accepted, and in the difference between the theory and observation is not significant, and there is no significant difference in the choice of the type of transportation. So, third, test of association or homogeneity. This type of chi-square is used for the two purposes. The first purpose is to examine whether or not the two or more attributes are associated. Test of association. The second purpose is to determine whether two samples are drawn from the same population or not. Test of homogeneity. In former case, the data is based on one sample, whereas in the later there are two or more samples. Chi-square, a non-parametric test, is a rough estimate of confidence. It accepts weaker, less accurate data as input than the parametric test. Like t-test and the analysis variance, and therefore has less status the pantheon of statistical test. Nonetheless, it is limitations are also its strength, because chi-square is more forbearing in the data it will accept. It can be used in a wide variety of researches. The step in the chi-square method for the test homogeneity remain the same as that of the test goodness of fit, except that in step 3, the expected frequencies are calculated for each cell as illustrated. Populations, attributes. Population 1, population 2, the categories A, D, B, C, D, F, N1, the number of occurrences. So expected frequency of cell A is N into N3 by N minus, okay, so N1 into, this is N1 into N3 by N. So expected frequency of cell B is N1, B, N1 and N4. This will be connected, C will be connected to N1 and N5, and D will be connected to N2 and N3. And E will be connected to N2 and N4, F will be connected to N2 and N5. And divided by N. So see in box 18.4 for an example to find out if there was a difference in the income of the two groups. On the basis of this example, you may take up another case to test the association homogeneity. Box 18.2 examples to examine if the bills and minars different in their income. Populations income group high, middle, low. Bills 28, 41, 65. Minas 31, 43, 55. Solution. Null hypothesis, there is no significant difference in the income between bills and minas. Alternative hypothesis, there is a significant difference in income between bills and minas. Probability level for the hypothesis testing is 5%. The expected frequency are as given below. So income groups observed and expected. So this is the way it has been calculated. Okay. And we can get these values of then chi square is equal to the sum of O minus E whole square by E. So after calculation we get it is 0.94. So degree of freedom, number of rows minus 1 plus number of columns minus 1. Multiply it to it will give 2. So step 6, the table values of chi square at 5% probability level for 2 degree of freedom is 5.991. The calculated value of chi square is 0.94, is lower than the table value of 5.9. Thus the null hypothesis is accepted and the difference between the theory and observation is non-significant, and there is no significant difference in the income of bills and minas. There is a shortcut method for the calculation of chi square if the frequency distribution arranged in 2 by 2 contingency table as illustrated in figure 18.3. Here only 2 by 2, only 2 rows and 2 columns. So in that case there is a shortcut method is to calculate is chi square is equal to n into a into d into minus b into c whole square by a plus b into c to d into a plus c and b plus d. Okay. So the calculated value of chi square examined against the tabulated value at 1D and f at a specified probable level to ascertain significance. See box 8.3 to find out the significant difference between the males and females in terms of their occupations. So this is the examples of to examine the significant gender-based differences of occupation as skilled and unskilled labor. Gender, males and females, how many are skilled and how many are unskilled. So here the step 1 is to form this null hypothesis and alternative hypothesis. Null hypothesis is to no significant sex difference is there, and the hypothesis and alternative hypothesis, there is a significant sex difference in skilled and unskilled labor. So the probability level for the hypothesis testing is 5%. So calculations when we do that as we done earlier in the short form, because this is 2 by 2 form. So shortcut form you do that 4.620, and the degree of freedom is also we can calculate as 1 because 2 minus 1 into 2 minus 1. So the table of chi square at 5% probability level, the 1 degree of freedom, it is 3.841. That chi square table we can see, and the calculated chi square 4.620 is higher than the table value of chi square. So we can say that the conclusion that the null hypothesis is rejected and the sex difference between the skilled and unskilled labor is significant, like that we can conclude. So fourth is students' tease test. Students' tease test is a parametric test most suitable for a small sample. It is probably the most widely used statistical test and certainly the most widely known. It is simple, straightforward, easy to use and adaptable to a broad range of situations. No statistical toolbox should ever be without it. Student, real name W.S. Gosset, developed the statistical methods to solve problems stemming from his employment in a brewery. Like chi square, the following steps may be followed for the use of students' test. First we have to define the null and alternative hypothesis. Second test, decide the probability level. Then third is calculate the values of t using appropriate formula. Then step 4 is determining the degree of freedom. Step 5 is compare the observed chi square with the tabulated chi square, accept or reject the null hypothesis. Then students test applied in the different condition as 1 to test the significance of the mean of random sample, to test the difference between the means of the two independent samples, to test the difference between the means of two dependent sample, to test the significance of correlation coefficient. Let us discuss each of the above conditions. To test the significance of the mean of a random sample, this test is used for the researchers is interested in examining whether the mean of a sample from the normal population deviates significantly from the hypothetical population mean. The following formula is used for its calculation. So T is m minus mu whole square n divided n, where when using actual mean, S is this formula when using the assumed mean. For S is this is the formula when R, M and mu are the means of sample and population respectively. N is the sample size, S is the standard deviation of the sample, small d is x minus a, x being the variable, and dm is the mean deviation, and a is the assured mean. Let us take an example in the box 18.4 of testing the mean nutritional intakes. Box 18.4, example to test the mean nutritional intake in the population with 200 calories. So this is the calories nutritional intakes, and solution is that null hypothesis. The mean nutritional intakes in this population for which the sample is drawn is 2000 calories. So alternative hypothesis, the mean nutritional intake in the population from which the sample is drawn is not 2000 calories. And step 2 is probability level of the hypothesis testing is 5%. Calculations. National intake calorie d is equal to x minus a, d square is this much. So we can calculate like that. And at the end we will, using this formula, above one formula, we can get the t is equal to 1.452. So and the degree of freedom is 10 minus 1 is 9, and the table value of t with the 5% probability level is 9 degree of freedom is 2.232. Then the calculated value of t 1.5 is lower than the table value of t, so 2.23. Thus the null hypothesis is accepted and the difference is not significant. The test to test the difference between the mean of the two independent samples. This test is used when the researchers is interested in examining whether the respective means of two independent samples differ significantly from each other. The following formula is used for its calculation. So this is t, the value t we can calculate is using the formula. When using actual mean, S is this formula, and when using assumed mean, S is a different formula, where d1 is x1 minus a1 and d2 is x2 minus a2, and respectively using the formula, and m1 and m2 are the respective means for the two types. So a1 and a2 are the assumed means of two samples, and n1 and n2 are the sample size, and S is the standard deviation. So we would take an example of in box number 18.5 to find out the Martial distance about among the Sandals and Murias. So examples to examining whether the Sandals and Murias differ in Martial stats, marital distance. So here the different values is given. Okay, and solution is that null hypothesis, Sandals and Murias do not differ in their marital distance. Alternative hypothesis are Sandals and Murias differ in their marital distance. Probability level for the hypothesis testing is 5%, and calculation is done like this in this as in the table. Okay, then we will get the t value as 3.036. So degree of freedom also here 10 plus 10 minus 2 is 18. So that is the degree of freedom, and the table value of at 5% probability level for 9 degree freedom is 2.101. Then calculated value is t is higher than the table value of t. So you can say that the null hypothesis is rejected and the difference in the marital distance between Sandals and Murias is significant. So third one is to test the difference between the means of the two dependent samples. This test is used when the researcher is interested in examining whether the mean of two dependent samples differ significantly from each other. The following formula is used for the calculations. So ready-made formula is given already. How it derived we don't know, we have to study that. So where d is x minus x2, dm is the means of the deviation, n1 and n2 are the sample size, and s is the common standard deviation. We would take an example in the box 18.6 to find out the difference in observation of the two researchers. So here in the box we have given two observers have taken an income of 10 households and examine whether this observation are differ significantly, because different people are taking the readings. Then we have to check whether this is there is any variation. So solution is first step as it is null hypothesis is there is a difference. The difference in observation of the two is significant, not significant, and alternative is there is a significant difference is there. Step 2 is probability level. The hypothesis is 5%, and then calculation we do that. Here as household 1 are to 10, and observer 1 is taken this reading, and observer 2 has taken this reading, and there is a difference what is this in the reading and their square. Then we can arrive the value of t using the formula as 0.958, and the degree of freedom also 10 minus 1 is 9. The table value t at 5% probability level, 9 degree of freedom is 2.232. So we can calculate also calculator value is 0.95 is lower than the table value. So you would say that the null hypothesis is accepted and the difference between the observers is not significant. So D, to test the significance of correlation coefficient, whether a coefficient of correlation is significant or not may be tested using the formula. Here also the formula is for T as given, where R is the coefficient of correlation and N is the number of observations, and degree of freedom is N minus 2. Here the notebook in box 18.7 we would take an example to test the importance of correlation. So this T is equal to R into V into N minus 2 divided by V into 1 minus R square. So here the example is using following data to test the significance of correlation. So R is 0.45 and N is 1.02. Null hypothesis that coefficient of correlation is not significant. Alternative is coefficient of correlation is significant. Probability level is 5%. Calculation of T we have done and we got this value as 5.039 as per the formula, and the degree of freedom is 10.1002 minus 2, that is 100. Then table values of T is 5% probability, 100 degree of freedom. We can see that 1.96. Then the calculated value 5.039 is coming. So it's very higher than the table value of 1.2. So thus we will find that the null hypothesis is rejected and the correlation is significant. So reflections and actions 18.3. Of the 4 tests in the section 18.4, select one test and carry out with respect to your own research work. Write it out in a detail in your research work report. So this is then will 18.5, the conclusion. Unit 18 has provided you with a range of ways to draw this inference. There are a good number of examples given for you to try and prepare for your examples. The exercise of working with as many as possible examples would help you to master the skills of testing hypotheses and estimating unknown parameters of the population. You need to keep in mind that no matter what design you use to test a hypothesis, you would reach only approximations in terms of probability. The testing of hypothesis prepares for you the ground for generating further hypotheses, and in this manner the scientific knowledge progress. Initial approximations put on firm basis of the original hypothesis, and from this you can further deduce other hypotheses. If you are able to establish link between the propositions, you would have generated scientific knowledge. Further reading, you have Handel, JD, Statistics for Sociology, and Watson, Statistical Inquiry, Elementary Statistics for the Political Science and Political Policy Sciences. This is the end of the